Hello dear students, all of you welcome to Vidyan classes. Today we will discuss the properties of inverse trigonometric functions. Property number 1. First bit. Sin inverse x is equal to x. X belongs to close bracket minus 1, 1 close bracket. Second bit, cos inverse x is equal to x. X belongs to close bracket minus 1, 1 close bracket. Third bit, tan inverse x is equal to x. X belongs to set of real numbers. Fourth, cot inverse x is equal to x. X belongs to set of real numbers. Fifth, sec inverse x is equal to x. X belongs to open bracket minus infinity minus 1 close bracket. Union close bracket 1 infinity open bracket. Cosec inverse x is equal to x. X belongs to open bracket minus infinity minus 1 close bracket union 1 close bracket 1 infinity open bracket. It is the first properties of inverse trigonometric function. Proof of second bit. Proof of second bit. Cos inverse x is equal to x. Cos inverse x is equal to x. Let cos inverse x is equal to theta. Every inverse trigonometric function represent a radian angle. Let cos inverse x equal to theta. Since cos so that close bracket 0 pi close bracket 2 my close bracket minus 1 1 close bracket is bijective. Every bijective function is invertible. That means its inverse is exist. Cos inverse so that close bracket minus 1 1 close bracket 2 close bracket 0 pi close bracket. Cos x is a cos so that close bracket 0 pi close bracket 2 close bracket minus 1 1 close bracket is bijective. So its inverse is exist. Cos inverse x equal to theta, that implies by x is equal to cos theta. Since cos function is bijective, when it is defined from this set to this set, its inverse is exist from this set to this set, which is same as cos. What is the value of theta? That is the cos inverse x. X equal to cos theta. Therefore, cos inverse x is equal to x. Cos inverse x is equal to x. X belongs to close bracket -1 and 1. It means x greater than equal to -1 less than equal to +1. That is x greater than equal to -1 less than equal to +1. Clear? Similarly, other properties can be proved. That is sin inverse equal to x, tan inverse equal to x. In this way, we can prove other 5 properties. Property number 2. E2. That means property number 2. First, sin inverse sin x is equal to x. Sin inverse sin x equal to x. What is x? X belongs to close bracket minus pi by 2 plus pi by 2. Second bit, cos inverse cos x is equal to x. X belongs to close bracket 0 by close bracket. Tan inverse tan x is equal to x. X belongs to open bracket minus pi by 2 plus pi by 2 this. Fourth, cot inverse cot x is equal to x. X belongs to open bracket 0 by open bracket. Fifth, sec inverse sec x is equal to x. X belongs to close bracket 0 pi by 2 open bracket union open bracket pi by 2 pi close bracket. Last, that is sixth bit, cosec inverse cosec x is equal to x. X belongs to close bracket minus pi by 2 g close bracket minus pi by 2 0 open bracket union open bracket 0 pi by 2 close bracket. Sin inverse sin x equal to x. If x belongs to close in this set, cos inverse cos x equal to x. If x belongs to this set, tan inverse tan x equal to x. If x belongs to this set, cot inverse cot x is equal to x. If x belongs to this set, sec inverse sec x is equal to x. If x belongs to this set, cosec inverse cosec x is equal to x. If x belongs to this set. All are discussed in the first lecture. These are the domain of the function. Proof of a second. Proof of a second. Cos inverse cos x is equal to x. Cos function is bijective when it is defined from this set to this set. That means its inverse is exist. That means its inverse is exist. Cos function is bijective when it is defined from this set to this set. Its inverse is exist. Cos inverse is defined from this set to this set. Let y is equal to cos x. Implied and implied by x is equal to cos inverse y. Inverse trigonometric function represent a radian angle. Plane trigonometric function represent a real number. Y is equal to cos x is a real number. When x varies from in this set, cos x is a real number. Cos 0 is equal to 1, cos pi is equal to minus 1. So cos x represent a real number, but cos inverse x represent a radian angle. X equal to cos inverse y. Since cos function is bijective. Cos is bijective when it is defined from this set to this set. Clear? Cos is bijective when defined this set to this set. Here the domain is this. Which is same as cos inverse. What is y? That is cos x. Y is equal to cos x. Since cos function is defined, cos function is bijective in this domain set, so we can write x is equal to cos inverse y is equal to cos inverse y. Cos inverse y means cos x. Therefore, cos inverse cos x is equal to x. X belongs to close bracket 0 pi close bracket. Clear? Similarly, other properties can be proved in the same way. Are you clear? Clear? Okay, note down. Property is 3. P3 means property is 3. First, sin inverse minus x is equal to minus sin inverse x. X belongs to close bracket minus 1, 1. Or x greater than equal to minus 1 less than equal to plus 1. Second bit, cosec inverse minus x is equal to minus cosec inverse x. X belongs to open bracket minus infinity minus 1 close bracket union close bracket 1 infinity open bracket, or if it is x, it is minus x. If it is x, it is minus x. So we can write it. X and minus x represent x mod. So x mod greater than or equal to 1. This is same as this. Third bit, tan inverse minus x is equal to minus tan inverse x. X belongs to R set of real numbers. Fourth, cot inverse minus x is equal to pi minus cot inverse x. X belongs to R set of real numbers. Sec inverse minus x is equal to pi minus sec inverse x. X belongs to open bracket minus infinity minus 1 close bracket union close bracket 1 infinity open bracket, or x mod greater than or equal to 1. Sixth, sin cosec tan cot sec cos. Cos inverse minus x is equal to pi minus cos inverse x. X belongs to close bracket minus 1, 1 close bracket. Sin inverse minus x is equal to minus sin inverse x. X belongs to close bracket minus 1, 1 close bracket. Cosecant inverse minus x is equal to minus cosecant inverse x. X belongs to this interval or x mod greater than equal to 1. Tan inverse minus x is equal to minus tan inverse x. X belongs to R. Cot inverse minus x is equal to pi minus cot inverse x. X belongs to R. Sec inverse minus x is equal to pi minus sec inverse x. And the cos inverse minus x is equal to pi minus cos inverse x. So, proof. Suppose third bit. Let tan inverse minus x is equal to theta. All inverse trigonometric functions are radian angles, which implies tan theta is equal to minus x. Tan so that minus pi by 2 plus pi by 2 open bracket minus pi by 2 open bracket to set up real numbers is bijective. Which implies by tan inverse is exist so that R set up a real number 2 open bracket minus pi by 2 pi by 2. In this interval, if tan is defined from this set to this set, it is bijective. Here x belongs to R. Here x belongs to tan inverse is defined from R to this. Implied and implied by. Or which implies and implied by x is equal to minus tan theta. Which is same as tan minus theta is equal to minus tan theta. Tan minus theta is equal to minus tan theta. X is equal to minus tan theta, which is same as tan minus theta, which implies and implied by minus theta. Since tan is invertible function, that is bijective, tan inverse x. Which implies and implied by theta is equal to minus tan inverse x. Which implies and implied by what is theta? Theta is equal to tan inverse minus x. Tan inverse minus theta is equal to tan inverse minus x is equal to minus tan inverse x. X belongs to R. Tan is the bijective function when it is defined from this set to this. Clear? Proof of last bit. Proof of last bit. Cos inverse minus x. Let cos inverse minus x is equal to alpha, where alpha is the radian angle. All inverse trigonometric functions are radian angles, which implies and implies by since cos so that close bracket 0 pi close bracket 2 open bracket minus 1 close bracket minus 1 1 close bracket, is by gt, is by gt implies and implies it by cos inverse such that close bracket minus 1, 1 to close bracket 0 by close bracket. Since cos is defined when x belongs to this, cos inverse is exist from when it is defined from this set to this set. Since cos is a bijective function in the given domain, since cos is the bijective function for the given domain, cos alpha is equal to minus x. Cos inverse minus x is equal to alpha, which implies and implies it by cos alpha is equal to minus x, as cos is the bijective for the given domain, x belongs to this, which implies and implies it by x is equal to minus cos alpha, which is same as cos pi minus alpha. Here cos pi minus theta is equal to minus cos theta. Which implies and implies it by pi minus alpha is equal to cos inverse x. Since cos is invertible for the given domain, which implies and implies it by alpha is equal to pi minus cos inverse x, which implies and implies it by what is alpha? Cos inverse minus x is equal to pi minus cos inverse. Clear? Cos inverse minus x is equal to cos inverse minus x is equal to pi minus cos inverse x when x belongs to close bracket minus 1, 1 close bracket. Hence proved. It is also hence proved. Similarly, other properties can be proved. Similarly, other properties can be proved. Are you clear? Okay, note down. Note down. Next, property 4. Property 4. Sin inverse 1 by x is equal to cosec inverse x if mod of x greater than or equal to 1. What is the meaning of mod of x greater than or equal to 1? That means x belongs to open bracket minus infinity minus 1 close bracket union close bracket 1 infinity open bracket. This is same as this. Second bit cos inverse 1 by x is equal to sec inverse x. X mod greater than or equal to 1. Third bit tan inverse 1 by x is equal to cot inverse x greater than 0 and minus pi plus cot inverse x if x less than 0. Sin inverse 1 by x is equal to cosec inverse x if mod of x greater than equal to 1. Cos inverse 1 by x is equal to sec inverse x if mod of x greater than or equal to 1, and tan inverse 1 by x which is same as cot inverse x greater than 0 minus pi plus cot inverse x less than 0. Proof. Suppose the second bit. Let y is equal to cos inverse 1 by x. Implies and implied by cos y is equal to 1 by x, which implies and implied by sec y is equal to x, equation 1. Since cos is invertible, sec y is equal to x. Y belongs to close bracket 0 pi close bracket minus set of pi by 2, which is same as close bracket 0 pi by 2 open bracket union open bracket pi by 2 pi close bracket. Since no real x exists for which y is equal to pi by 2. That is, for y is equal to pi by 2, one by x is equal to 0. Cos 90 degree is equal to 1 by x. Cos 90 equal to 0 implies x tends to infinity. Not real. So no real x is exist for which y is equal to pi by 2. At x is equal to pi by 2, 1 by x is equal to 0. That means x tends to infinity, which is not real. Clear? Okay. We have to show cos inverse 1 by x is equal to sec inverse x. Y belongs to close bracket pi close bracket 0 pi close bracket minus set of pi by 2, which is same as close bracket 0 pi by 2 open bracket union open bracket pi by 2 close pi close bracket, which is same as what is the range of sec inverse x? It is the range of sec inverse x. Since sec inverse x is bijective when it is defined from this set to this set. Sec inverse x is defined when it is defined from this set to this set, which is same as range of sec inverse x. So equation 1 implies the inverse of sec is exist sec inverse is exist y is equal to sec inverse x. What is y? Y means cos inverse 1 by x is equal to sec inverse x. Condition mod of x greater than or equal to 1. Y is equal to cos inverse x, cos y is equal to 1 by x. Here cos inverse is exist, so we can write cos y is equal to 1 by x or sec y is equal to x. What is the range of cos inverse 1 by x? It is the range of cos inverse 1 by x or this set, since no real x exists for which y is equal to pi by 2. For y is equal to pi by 2, 1 by x equal to 0. That implies x tends to infinity, which is not real. So y belongs to this set. Y belongs to this set or this set. It is the range of sec inverse x. It is the range of sec inverse x. That means sec is invertible. It is sec is defined from this set to this set. It is the domain of sec inverse x and it is the range of sec inverse x. So sec is invertible. Equation 1 implies y is equal to sec inverse x. It is given by y is equal to cos inverse 1 by x, which is equal to sec inverse x, hence proved. Hence proved. Similarly, first bit and third bit can be proved. Example, cos inverse half is equal to sec inverse 2. Cos inverse half is equal to sec inverse 2. All inverse trigonometric functions represent an angle. Which angle of cos that belongs to this set? That belongs to this set whose value is cos value, is 1 by 2. It represents an angle that is equal to pi by 3. That means 60 degree. Cos inverse half, cos 60 degree is equal to pi by 3. Inverse trigonometric function represent a radian angle. Cos inverse half is equal to sec inverse 2. By this rule, cos inverse 1 by x is equal to sec inverse x. But cos inverse 1 by x represent a radian angle, which angle of cos that belongs to this set having cos value half. Which angle of cos that belongs to this set having cos value half, that is 60 degree. Example 1. Example, suppose 2 tan inverse 1 by root 3 which is equal to pi by which angle of tan? Which angle of tan that gives value 1 by root 3. Here 1 by root 3, since 1 by root 3 greater than 0. Which angle of tan which gives value or which is same as cot inverse root 3. Which angle of tan which gives value 1 by root 3, that is 30 degree, pi by 6. Or which angle of cot gives value root 3, that is tan 30 degree is equal to 1 by root 3, cot 30 degree is equal to tan 30 degree is equal to 1 by root 3. Or cot inverse root 3, tan inverse 1 by root 3 is equal to cot inverse tan inverse 1 by x is equal to cot inverse x when x greater than 0. Which is same as, since 1 by root 3 greater than 0, which angle of tan that gives value 1 by root 3, that is pi by 6, that means 30 degree. Clear? Are you clear? Okay, note down. Next property 5. Property 5. Sin inverse x plus cos inverse x is equal to pi by 2 if mod of x less than or equal to 1, that is x greater than equal to minus 1 less than equal to plus 1. Second, tan inverse x plus cot inverse x is equal to pi by 2 if x belongs to R, set up a real numbers, that is x belongs to open bracket minus infinity plus infinity open bracket. Third bit, sec inverse x plus cosec inverse x is equal to pi by 2 x mod greater than or equal to 1, that is x belongs to open bracket minus infinity minus 1 close bracket union close bracket 1 infinity open bracket. Sin inverse x plus cos inverse x is equal to pi by 2 when mod of x less than equal to 1. Tan inverse x plus cot inverse x is equal to pi by 2. X belongs to set of real numbers. Sec inverse x and cosec inverse x is equal to pi by 2 if mod of x greater than or equal to 1. Proof. Suppose the first bit. Let y is equal to sin inverse x, which implies it by x is equal to sin y, which implies it by x is equal to cos pi by 2 minus y. It is equation 1. Since sin so that close bracket minus pi by 2 plus pi by 2 close bracket 2 close bracket minus 1 and 1 is bijective, which implies it by sin inverse so that close bracket minus 1 close bracket 2 close bracket minus pi by 2 plus pi by 2 close bracket. If sin function defined from this to this, the function is bijective, that means invertible. Its inverse is exist, sin inverse is defined from this set to this set. Range of sin inverse is this. Y is equal to sin inverse x. Sin inverse x represents the principal value or range. Y belongs to, this is y, belongs to close bracket minus pi by 2 plus pi by 2 close bracket, which implies y greater than equal to minus pi by 2 less than equal to plus pi by 2. Minus y greater than equal to minus pi by 2 greater than equal to plus pi by 2 greater than equal to, multiplying minus sign everywhere, pi by 2 greater than equal to minus y greater than equal to minus pi by 2, which implies minus y greater than equal to minus pi by 2 less than equal to plus pi by 2. Adding pi by 2 everywhere, it gives 0, pi by 2 minus pi by 2 0, pi by 2 minus y, pi by 2 plus pi by 2, that is equal to pi. Since cos so that close bracket 0 pi close bracket 2 close bracket minus 1 1 is bijective, implies it by cos inverse so that close bracket minus 1 2 close bracket 0 pi close bracket. Since cos is bijective from this set to this set, its inverse is exist and cos inverse is defined from this set to this set. Pi by 2 minus y belongs to, which implies pi by 2 minus y belongs to close bracket Now pi by 2 minus y belongs to close bracket 0 pi. Close bracket is 0 pi close bracket, which is equal to range of cos inverse x, which is equal to range of cos inverse x. Cos function is bijective from this set to this cos inverse range of cos inverse, so that close bracket minus 1 to 1 to close bracket 0 pi close bracket. Pi by 2 minus y belongs to pi by 2 minus y belongs to this set, which is equal to range of cos inverse x. Since this belongs to this set, equation 1 implies this. That means equation 1 implies pi by 2 minus y is equal to cos inverse x. Since cos inverse is cos function is bijective when it is defined from this set to this set, and cos inverse is the function from this set to this set. Range of cos inverse x is close bracket 0 pi. Since pi by 2 belongs to this, the function cos function is invertible, so we can write equation 1 implies pi by 2 minus y is equal to cos inverse x. It is equation 2. Sin inverse x plus cos inverse x, which is equal to sin inverse x is equal to y, cos inverse x is equal to pi by 2 minus y, which is equal to pi by 2. Therefore, sin inverse x plus cos inverse x is equal to pi by 2. When x mod less than equal to 1. Similarly, second and third be hence proved. Similarly, second bit and third bit can be proved. Example, sin inverse k is equal to alpha and cos inverse k is equal to beta, where k mod less than or equal to 1. Find the relation between alpha and beta. Sin inverse k is equal to alpha, sin inverse k is equal to alpha, cos inverse k is equal to beta, where k less than or equal to, where mod of k less than or equal to 1. Answer. Sin inverse x plus cos inverse x is equal to pi by 2. Sin inverse k plus sin inverse k is equal to pi by 2. At what condition? Is equal to pi by 2. Since sin inverse x plus cos inverse x is equal to pi by 2 x mod less than or equal to. So sin inverse k plus cos inverse k is equal to pi by 2 k mod less than or equal to 1. K is replaced by x. Since sin inverse x plus cos inverse is equal to pi by 2, when mod of x less than or equal to 1, x is replaced by k, x is replaced by k, and k mod of k less than or equal to 1. So sin inverse k plus sin inverse k plus cos inverse k is equal to pi by 2. Sin inverse k plus cos inverse k is equal to pi by 2 when mod of k less than or equal to 1. Since sin inverse x plus cos inverse x is equal to pi by 2, here x is replaced by k, sin inverse k plus cos inverse k is equal to pi by 2, which implies this sin inverse k is equal to alpha and cos inverse k is equal to beta. So alpha plus beta is equal to pi by 2 is the relation between alpha and beta. Find the relation between alpha and beta. Alpha plus beta is equal to pi by 2. Clear? Okay, note down.